Welcome to the Deep Dive, where we short-circuit the research process and deliver the critical insights you need. Today, we're diving into a really fundamental problem in scaling AI. What happens when the engine of modern AI, backpropagation, just breaks?
It's a huge limitation. Backprop needs everything to be smooth, continuous, differentiable. But so many interesting real-world problems just aren't like that. Think about optimizing over discrete choices or just learning from a final score, a reward signal. That's the world of black box optimization.
And in that world, the reigning champion has always been evolution strategies, or ES. ES doesn't need gradients. It just sort of wiggles the model's parameters, sees what works better, that's the scalar fitness, and learns from that trial and error across a whole population.
And because every one of those trials is independent, it's theoretically, massively parallelizable. You can spread it across thousands of GPUs.
It sounds perfect. It's robust. It can handle messy situations like vanishing gradients and recurrent networks.
It really should be the go-to solution for training at huge scales.
But, and this is the big roadblock we're tackling today, standard ES has this crippling weakness when you try to use it on a modern model with billions of parameters. The math itself just kills the whole idea.
Right. The problem is how ES explores. To create all those little parameter shifts or perturbations for the population, it has to generate a massive, full-rank random matrix. Let's call it E.
And what are the dimensions we're talking about for E?
Well, think about a single-weight matrix in one layer. It might have an input dimension, say M, and an output dimension, N. So the perturbation matrix E has to be the exact same size, M by N.
And M and N can be huge, like tens of thousands.
Exactly. So the cost of just generating, storing, and then applying that giant matrix, it scales with OPM. It's just way too expensive.
For every layer, for every single worker in your cluster, you're talking about sending a billion numbers around for every single update. The whole parallelism advantage just evaporates.
It's a total non-starter.
So, our mission today is to figure out how a really clever paper called Evolution-Guided General Optimization via Low-Rank Learning, or just EGGROLL, cracks this problem. They use a beautiful mathematical trick that delivers supposedly 100-fold speedup.
It's a fantastic insight. EGGROLL's core idea is that we don't need that full-rank perturbation matrix E. We can approximate it by multiplying two much, much smaller random matrices.
Okay, so break that down for us mathematically. What does that look like?
Instead of sampling this huge M by N matrix, E, you sample two skinny ones. One is A, which is M by R, and the other is B, which is N by R. The full perturbation E is then just their outer product, A times B transpose.
And the key here is R, the rank. And R is tiny, right? We're talking like 1 or 4 or maybe 10. Compared to M and N, which could be in the thousands.
It's a massive compression. It's really the same idea behind low-rank adaptation, or LoRa, that people use for fine-tuning, but here it's being used for the actual search process.
So let's talk numbers, because this is the key takeaway. In standard ES, the storage you need is proportional to M times N. What does EGGROLL bring that down to?
It drops all the way down to R times M plus N.
Yeah.
And the compute cost does the same thing. It goes from OMN down to ORM plus N.
So you're swapping a quadratic cost for a linear one. That's where the 100-fold speedup comes from.
That's it.
But that raises a huge question for me. If every single perturbation you generate is super low rank, aren't you, crippling the search? It feels like you're only looking along this one tiny constrained line in a space with billions of dimensions.
And that is the most elegant part of this whole thing. It's true that each worker's individual perturbation is low rank, but the final update to the model, that's an average of all the fitness-weighted perturbations from the entire population of N workers.
So the update itself isn't a single ranker matrix.
Precisely. The final update matrix has a rank of, get this, the minimum of NR, M, or N.
Okay, and since N, the population size is huge in EGGROLL.
Right, we're talking hundreds of thousands.
Sure.
So N times R is almost always going to be way bigger than M or N. This means the overall search direction is still high rank. It has all the richness and power you need.
So you get cheap calculations for each worker, but you keep the powerful high-rank exploration for the whole population. That's brilliant.
It is, and it has real hardware benefits, too. This structure lets them use highly optimized GPU kernels, the kind of thing used for batched LoRa inference. So the speedup isn't just theory, it's practice.
All right, we have the speed, we have the memory savings. Now, for the really deep mathematical part of this, does this low-rank approximation actually work? I mean, does it compromise the quality of the final solution?
This is where the paper gets really interesting. They had to prove that this approximation error, the difference between their method and the true full-rank search, shrinks really fast as you increase R. And their key theoretical finding, Theorem 2, shows that the EGGROLL update converges to the full-rank version at a rate of O1.
O1R. Okay, for those of us who aren't deep in convergence theory, why is that special? What would we normally expect?
Typically, when you're doing this kind of approximation, averaging samples to get to a target distribution, the central limit theorem tells you the error should decay at a rate of O first is QRTR.
So O1R is a lot faster than O first QRTR.
Yeah.
It's a huge difference. How did they get this mathematical cheat code?
It all comes down to a very, very clever choice about the probability distribution they used to sample the small matrices A and B. It's related to a concept called cumulants.
Cumulants. Okay, those are the things that describe a distribution's shape, right? Like beyond just the average and the spread.
Exactly. And the key is their first assumption in the proof.
Yeah.
They draw all the random numbers for A and B from a distribution that is zero, mean, and, crucially, symmetric.
Why is symmetry the magic ingredient?
Because in probability theory, a symmetric distribution has all of its odd-order cumulants equal to exactly zero. The most important one here is the third-order cumulant, which describes skewness or lopsidedness.
Okay, so if that third-order term is zero, how does that make things converge faster?
Well, that slower Foerster convergence rate that we usually see, it's directly caused by that third-order term. It's the main source of what you could call statistical drag.
Yeah.
By designing their system to be symmetric, they just delete that term. It's gone.
So they mathematically engineered away the slowest part of the convergence process.
Yes. So the convergence is now controlled by the next term, the fourth-order cumulant. And that term decays much faster at that beautiful O1R rate. It's just a really elegant piece of analysis.
And they show this in a graph, right? Where even for a tiny rank like R10, the distribution looks almost identical to the perfect one.
It does. It just confirms the theory. You don't need a big rank to be accurate, which is great because you need a tiny rank to be fast.
Okay, with that theoretical foundation in place, let's move to the applications, because this is where things get really wild. They created a model called the Evolved Generative GRU, or EGG, and they used it to pre-train a language model under conditions that would be just impossible for gradient descent.
Yeah, the EGG model was designed from the ground up for pure hardware efficiency, with two huge constraints.
The first one being pure integer training.
Correct. The whole thing runs on integers. int8 weights, int32 activations. No floating point numbers, ever. This is amazing for speed on modern hardware, but it's a nightmare for gradients. ES doesn't care, though.
And the second constraint, which honestly blew my mind, is that they removed all the standard activation functions. No ReLU, no TON, nothing. How does a deep network even learn without nonlinearity?
This is the radical part. The nonlinearity comes from the hardware itself. When you do math with int8 numbers, if the result goes outside the very narrow range of values it can represent, the hardware just clips it. It's called saturated addition.
Wait, so the hardware limitation, the clipping, is the nonlinearity that the evolution strategy learns to use.
That's it exactly.
Yeah.
It's treating a bug as a feature. A black box optimizer like ES doesn't need a neat mathematical formula for the nonlinearity. It just needs to see that the outcome works. This let them train stable recurrent models on incredibly long sequences.
And this efficiency allowed for a truly massive population size.
Unprecedented, really. The previous big ES paper from a few years back maxed out at about 1,440 workers. EGGROLL used a population of up to 2 to the power of 18. It's over 262,000.
2 orders of magnitude more.
It's a different world. And their experiments showed you need that scale. They found that for pre-training, performance was all about maximizing the number of unique perturbations. You need that huge parallel search.
Which means that just trying to do this with a population of 1, so-called zeroth order optimization, is basically useless for a task this complex.
That's the clear message. You need the whole population.
And moving to the benchmarks, it wasn't just fast, it performed. In reinforcement learning, even with a tiny rank of 1, it was competitive or better than standard methods on most environments.
And then came the big test, fine-tuning a 1.5 billion parameter recurrent language model for reasoning tasks.
Right, they put EGGROLL up against another method, GRPO.
And on the countdown reasoning task, with the same amount of time on the hardware, EGGROLL hit 35% accuracy. GRPO only got to 23%. That's a huge performance lift for the same time budget.
And the throughput numbers just seal it. If you say pure fast inference is a speed of 100, EGGROLL clocks in at 91. It's almost as fast as just running the model. Standard OpenES was down at 0.41.
That's the 100-fold difference right there. It's what makes this a practical tool, not just a theoretical curiosity.
So to wrap this all up, EGGROLL is a monumental step. It takes evolution strategies, which was always stuck because of this OMM scaling problem.
And it completely unlocks it for billion-parameter models using this elegant low-rank trick.
Giving them linear scaling, ORM plus N.
And critically, they prove the approximation is incredibly accurate thanks to that fast ONR convergence, which they got by being very clever about symmetry in their math.
The big implication here seems huge. EGGROLL's ability to handle things that aren't differentiable at scale, that seems to unlock a whole new class of AI systems.
I think so. Right now, we're stuck when we try to connect big neural nets to other specialized modules, things like an external memory or a search algorithm or a calculator. Those things often aren't differentiable, so gradient descent just breaks.
But EGGROLL wouldn't care.
It wouldn't care at all. It makes it possible to train these massive, powerful, hybrid neurosymbolic systems from end to end. It's a step beyond what gradients can even do.
So what stands out to you about a future where every part of a complex intelligence system, even the clunky, non-differentiable parts, can be trained at nearly the speed of inference? We'll leave you with that thought.